Alright, pre-AP Chemistry, this is the stoichiometry notes part 2. So we're ready to move on here. And I first of all have a little graphic for you. This is called Mole Island. And you see the lovely moles. And basically what the stoichiometry is and what Mole Island is dealing with conversion factors. How do you go from how much substance you have, how much stuff you have of one substance, to figuring out how much stuff you're going to make of another substance? Or in any format, how do you relate substances in a chemical equation? And what you do is you have conversion factors. You already know that 1 mole of a substance is equal to the molar mass of the substance. So that's one conversion factor. You also know that we could figure out how many particles or atoms or molecules of something we have because 1 mole of a substance is equal to 6.02 times 10 to the 23rd particles. A new one for you, and again I just mentioned this on the part 1. 1 mole of a substance of a gas at STP, that's standard temperature and pressure, is equal to 22.4 liters of that gas. Okay, now Mole Island is someone, I'm not sure who came up with this, but it's a really cool little idea. Basically, what you have is, you have on the left-hand side of the chart, this is the stuff you start out with, and on the right-hand side of the chart, this is the stuff they're asking you about over here. So what you have here is, let's say they start off and they say, oh, well, we've got 10 grams of this substance. Well, you know how to change grams to moles, so that's not a big problem at all. How do you go from moles of one chemical to moles of another? Well, what you do is you use the balanced chemical equation. If you have a volume like a gas at STP, it's going to be 22.4 liters. That's your conversion factor. So if you start out with X number of liters of one, you can change from the volume to the mole because 1 mole of a gas at STP is equal to 22.4 liters. Or you can go from particles to moles using Avogadro's number. Let's move on. Here is the same thing, only it's telling you here what conversion unit you're using. So if you want to go from mass to moles, you use the molar mass of a substance. If you want to go from volume of a gas at STP to moles, you use 22.4 liters is equal to 1 mole. If you want to go from particles, you use Avogadro's number to get to moles. And always, 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 when you go from moles of one substance to moles of another in one chemical reaction, you use the coefficients from the balanced chemical equation. Because we talked about in part 1 that you can look at a balanced equation and look at it in terms of 2 moles of this plus 3 moles of that yields 1 mole of this other substance over here. Okay? And once you have converted from moles of one substance to moles of another, you already know how to go from moles to grams, or moles to particles, or in this case, the new one, moles to the volume of a gas. Okay, and here it is again, just another pretty picture. And if you like this diagram, I'll print one of these off so you can have this diagram to use if it makes sense to you. Another diagram, and I like this one too, another diagram deals with the same basic thing, only here we have volume. Come on, go back. There we go. Here we have volume of a gas at STP, and if you're going from volume to moles, it tells you, hey, look, 1 mole of a gas at STP is 22.4 liters. That would be from old Avogadro there. Figured out that, hey, if you have a certain amount of, if you have 1 mole of any gas, if you have a certain number of particles, any gas of any kind is going to have the same number of particles if they're at STP. So same volume of gases have same number of particles at STP. So if you want to go from moles to get to volume of a gas, then you use the 22.4 liters over 1 mole. And again, this one has little scales for the mass, and then over here you have little square particles over here. So if you like this one, I can run a copy of this one off for you too. So it just kind of gives you a visual to go along with all the math that we're going to be doing. Okay, so you've got if you look at your equation up here, your balanced chemical equation, you've got 2 moles of aluminum oxide, and we're going to decompose that decomposition reaction into 4 moles of aluminum atoms, or 4 moles of aluminum, and 3 moles of oxygen. Each time we use 2 moles of the aluminum oxide, we're going to make 3 moles of oxygen, right? That makes sense. So we have a conversion factor. We can put 2 moles of aluminum oxide on top and 3 moles of oxygen on bottom, or we can just swap those. And so we can use that the same way, because it's kind of like saying 2 is equal to 1 times 2. So they look different from each other. You can put 2 on top and 1 times 2 on bottom, or you can flip that because they are the exact same quantity. Here, again, we're just using conversion factors. Kind of like 12 inches is equal to 1 foot. They don't look the same. You don't write them the same. but they're in equal quantity. So these are our two possible conversion factors on this one, if we're just talking about from one to the other. So your question is, how many moles of oxygen are produced when 3.34 moles of aluminum oxide decompose? Well, you've got the balanced chemical equation. You must have the balanced chemical equation. Sometimes the problem gives you the balanced equation. Sometimes you have to balance the equation. And sometimes you have to write the entire equation and then balance it. It just depends on what you've got going. You guys will do all of these at some point. So you've got to start with the balanced equation, and you've got it right there. So that's not a problem. So the next step you want to do is write down what they gave us. They gave us 3.34 moles of aluminum oxide. So somewhere on your paper, oh, you have a little bit of space there, don't you? Ooh, it's got, oh no, it's a different problem. I said, yeah, there's a little space up there. Okay, I figured out where I am here. You've got some room there. If you don't have enough room, then get yourself a scratch sheet of paper and put it with this. So write down what they gave you. They gave you specifically 3.34 moles of aluminum oxide. You must write down the substance that goes. Don't just write down 3.34 moles. Write down 3.34 moles and put Al2O3, because you're going to convert from one substance to another. Because they're going to say, and the question flat out asks you, how many moles of oxygen? So you're going to have to change from aluminum oxide to oxygen. How do you do that? Look at your balanced chemical equation. Remember that whatever is up here must go down here to the corner. So we're going to have to put the moles of aluminum oxide down here because that's what we want to cancel out. How many moles of aluminum oxide do we have from the balanced chemical equation? Right here's what we're looking at. So we want the 2 moles of aluminum oxide down on the bottom, and for every 2 moles of aluminum oxide, there are 3 moles of oxygen. Why did we put oxygen there? Because our question says, how many moles of oxygen? So right now, look at what cancels out. We have moles of aluminum oxide on top, we have moles of aluminum oxide on bottom, and hallelujah, they cancel out. So you've got 3.34 times 3 divided by 2. And that gives us 5.01 moles of oxygen. So how many moles of oxygen are produced when 3.34 moles of aluminum oxide decompose? Well, that would be 5.01 moles. Now, that's on paper. In reality, in the lab, you're probably not going to get that nice, perfect little amount there because everything isn't going to be perfect in the lab. There's always room for error. You're always going to lose some substance. It's not going to be perfect. So we have the theoretical or calculated value, and then we have the lab or actual value. Next one, you have the practice here is, and this has room, you have room for this on your paper, C2H2, so 2 moles of C2H2 plus 5 moles of oxygen is going to produce 4 moles of carbon dioxide and 2 moles of water. And of course, this is a combustion reaction, combustion of a hydrocarbon, so we always have 2 products, carbon dioxide and water. So if 3.84 moles of C2H2 are burned, how many moles of oxygen are needed? Always start off, write down what they gave us. That's the answer. Woo! Okay, let me backtrack. We're going to have to do this on paper then. Actually, I'm going to have to see if I can do this on the board here. So let's see. It froze up on me last time. I'm hoping it doesn't freeze up on me and I have to do this all over again. I won't be happy about it. So here's my pen. So I'm going to write down, first of all, what did they give us? They gave us 3.84 moles of C2H2. Draw my lovely crooked line. Now, oh, I don't need my line that long, so I got a little carried away there, right? So I want to go from moles of C2H2 to moles of oxygen, because that's what they're asking me. So moles of C2H2. Look at the balanced chemical equation, and the balanced equation says I have 2 moles of C2H2, and I want to change to oxygen, and for every 2 moles of C2H2, I've got 5 moles of O2. So 3.84 times 5 divided by 2, pop it into your calculator, and it should be the stuff, the 9 point something that we saw on there earlier. Okay, so let's erase all the ink on the slide. Change it back to an arrow. Let's see if it'll work. So we get 9.6 moles. Hopefully that's what you came out with on your paper. Now you guys typically are supposed to keep 2 digits to the right of the decimal, so I don't know what's going on here. Alright, next problem. How many moles of C2H2 are needed to produce 8.95 moles of H2O? Sometimes we can take kind of a shortcut here. Look at the mole ratio. C2H2, we've got 2 moles of C2H2, and they're asking us about water. We've got 2 moles of H2O. So that's a 1-to-1 mole ratio. So if we're just talking moles, right, this mole and this mole number should be the same. So if this mole says 8.95, then we ought to end up with 8.95 moles of water. Since that's a 1-to-1 mole ratio between these two, then you know that you're going to have 8.95. If that doesn't make sense to you, then all you have to do is do the math. Write down what they gave us. They gave us 8.95 moles of C2H2. We use the conversion factor. We've got 2 moles of C2H2. This is straight from the balanced chemical equation for every 2 moles of water. Look what happens. Our moles of C2H2 cancel out, so all we have left are moles of water. 2 cancels out, 2 cancels out, so all we have left here is 8.95. 8.95 what? 8.95 moles of water. Okay, next one. If 2.47 moles of C2H2 are burned, how many moles of carbon dioxide are formed? Go back up here, and since we can only do this when we go mole to mole, when we go mole to mole ratio, it's actually a little bit easier than anything else. You notice we have the C2H2 right here, and we're going from the C2H2 to the carbon dioxide. Look at the mole ratio. This one, the CO2, is always twice as much as this, so it should be, if we take 2.47 times 2, we should get 4.94 moles, which is how many moles of carbon dioxide that we'll get. Again, if it doesn't make sense to you, then write down 2.47 moles of C2H2, and then use our conversion factor. 2 C2H2 on bottom, 4 CO2 on top, and you can multiply that out. How do you get good at this? The absolute only way to get good at this is to practice. And I, as your loving teacher, will give you much practice. Alright, so here are the general steps in calculating the stoichiometry problems. 1, balance the equation. We must start out with a properly balanced equation. 2, convert grams to moles. You're going to always go from grams to moles. Set up the mole ratio. Use the mole ratio to calculate the number of moles desired. So, and this is kind of you could actually combine steps 3 and 4. When you set up the mole ratio, what you're basically doing is using the balanced equation to go from moles of one substance to moles of the other, and ultimately you're going to convert back to grams if the question asks you that. Alright, so here's what a typical question looks like. You've got 6.5 grams of aluminum. It's going to react with an excess. You've got lots and lots of oxygen. How many grams of aluminum oxide are formed? So there's your balanced chemical equation. You've got it written out for you. I strongly suggest that you write this one out on your scratch sheet of paper. This is a great example of one. So what do we start off with? If you look at the problem, there's only one number that they gave us. So we have to start off with 6.50 grams of aluminum. So write down your 6.50 grams of aluminum. Make sure you put what substance you're dealing with. We have to go from grams of aluminum to grams of aluminum oxide. So we can't do squat when it's in gram form. We must have it in moles. So we go from grams of aluminum to moles of aluminum. How do you do that? Use the formula mass. So we've got 26, and I know it should be 27, but I didn't retype this one. So we've got 27 grams of aluminum is equal to 1 mole of aluminum. So by doing that, we're able to cancel out the grams of aluminum and what we have left. If we were to stop right here, our answer would be in moles of aluminum. They don't want moles of aluminum, they want grams of aluminum oxide. So we've got to take another step. We have to convert now that it's in moles. We can go from moles of one substance to moles of any other substance in that balanced chemical equation. So we're going to go from moles of aluminum to moles of aluminum oxide. So there are 4 moles of aluminum for every 2 moles of aluminum oxide. Notice now that our moles of aluminum cancel out. And if we stop here, our answer would be in moles of aluminum oxide. But if you look at the question, it says how many grams. So now what we have to do is take that mole, those 2 moles of aluminum oxide, and convert them to grams. How do we do that? We use the formula mass. We've got 1 mole of aluminum oxide for every 102. That should be 102 rounded up because I told you to round all the numerals from the periodic table. So 102 grams of aluminum oxide. Notice again that our moles of aluminum oxide cancel out, and so now our only units of measurement that are left are grams of aluminum oxide. So you're going to multiply everything across the top divided by everything on the bottom. I strongly suggest that when you put this in your calculator, you want to make sure it's done properly. Open parentheses here, close oops, I can't write that one. Close parentheses there. Ew, that's a nice scribble. Hit divide. Open parentheses, type it all in, close parentheses right over here, and then hit enter. So put your parentheses in there, make sure you're doing it right. Erase all ink. And get rid of that. Right. And let's see, so we've got 6.5 times 2, we don't care about the ones, times 102, divided by, open parentheses, 27, times 4, close parentheses, and we should get somewhere around 12.3. It'll be slightly different because the answer here used all the little digits to the right of the decimal, which you don't need to. So that's our mass problem. One more example, and this one's going to be really important to you, especially when you do the lab that we're doing, I think it's tomorrow. So, if 10.1 grams of iron are added to a solution of copper 2 sulfate, how much solid copper would form? So your balanced chemical equation is written out for you. Let's see if I can write on this and it not freeze up on me. So let's do the pen. So what did they give us in the problem? They gave us this. That's what you need to write down first. So 10.1, I'm having ink problems, grams of iron. Can't do squat with grams, so we have to change it to moles. How do I change it to moles? I use the periodic table, and I've got 56 grams of iron is equal to 1 mole of iron. Now I've got it in moles. You notice that because look at the grams of iron here, grams of iron here. That's a 1. Okay? So they don't want moles of iron, though. They want how much solid copper. Usually when they say how much, they're talking grams. So they want to go from iron to copper sulfate. So for every 2 moles of iron, there are 3 moles of copper sulfate. So, oh, wait. How much solid copper? Okay, you got to make sure you know what it is they're asking you. So solid copper. So 2 moles of iron. And for every 2 moles of iron, we have 3 moles of copper. Again, moles of iron cancel out, and right now if we stopped, we'd have moles of copper, but they're asking us how much, and usually that indicates grams. So now I've got to change this 3 moles of copper into grams. So for every 1 mole of copper, there are how many grams? 63. Is it 63.5? I guess it is. 63.5 grams of copper. Notice the moles of copper cancel out, and now the only unit of measurement we have left are grams of copper. So whatever our answer is going to be, it's going to be grams of copper. Start off and open your parentheses right here. That's a 1, 0. I know that's pitiful. 1, 0. And close your parentheses here. Hit divided by, then open your parentheses. Close your parentheses. Right? Let me erase all this. You better have gotten it down. Let's see. Erase all the ink on the slide. That was a sound effect. Yeah. Alright, so let's see what we've got here. Answer should be right around 17.2. And again, it's possible I used all the digits on the periodic table, so that might not be exactly what you guys have. I did not redo the problem. Okay, you have several mass problems to do. That's what you need to work on.